Hey everyone! Today I want to talk about optical interferometry, a method that is frequently used to measure the properties of optical components and systems. What initially made me want to do a video about this subject is this ZYGO interferometer that I bought a while ago second-hand. A new instrument of this type is financially far out of my reach, and I must admit that this one wasn't a bargain either. But the thing is, I've wanted to own a high quality interferometer for a long time, if only to get away from the do-it-yourself setups that I've used so far. And since these instruments are not abundantly available second-hand, I just had to take this rare opportunity to buy one. In case you have no idea what this instrument is, with it you can very accurately measure the shape of flat and spherical optical interfaces, like the ones you find on lenses and mirrors. And with accurately I mean in the nanometer range. But not only that, you can also measure the performance of complete optical systems. So a good interferometer is an indispensable tool for anyone involved in optical fabrication, because in the end the quality of your optics is mainly limited by the quality of your testing methods. This particular instrument was produced by ZYGO in August of 1996. It was sold to Philips Electronics in Eindhoven, where it was used to check the surface shape of lenses of special optical disc drives. From what I understood, some of these lenses were produced from small polished glass balls, and these were cut in pieces and then transformed into very short focal distance lenses. Now at some point the activity was transferred to a Philips spin-off called Anterion, and the interferometer was sold to an employee who basically stored it for a couple of years. He then sold it to me together with a black and white monitor and the transmission sphere that was used to test the lenses. In this video I'll first discuss the principle behind interferometry, and then we'll take a look at the layout of the instrument and how it works exactly. And in an upcoming video I'll show you how I pimp the instrument a bit with a modern CCD camera. As I said earlier, in optics manufacture, interferometry is a frequently used method to characterize both optical surfaces as well as complete systems. And the method is based on analyzing interference patterns and extract so-called wavefront information from them. And I will discuss the meaning of the word wavefront in a second. Now, interferometry is an extremely sensitive and accurate method that can be used to establish the general shape of an interface, but also things like waviness or even surface roughness. It does also have some limitations. The measurement range is generally fairly limited to several microns. Also, it's unsuitable for interfaces that contain sharp step-like height features, because these cannot be unambiguously identified. And so, in general, interferometry is most accurate when the surfaces we want to test are fairly smooth. Now, I just mentioned the word wavefront, which I think is not a trivial concept. I guess we've all experienced wavefronts at some point in our lives, but I'm not referring to those. In optics, a wavefront is actually a continuous set of points that have identical phase. So what does that mean? Well, from a classical viewpoint, light is an electromagnetic wave that harmonically oscillates and propagates in space. And at any given point in this process, the electric and magnetic field components can be described by the Maxwell equations. So here I've tried to schematically draw the electromagnetic field in a somewhat larger volume, and if you examine the phase of these waves, you can identify planes where the phase of the electromagnetic field is identical, and the continuous set of points that have the same phase value is called a wavefront. One property of a wavefront is that its shape is always transverse or perpendicular to the local direction of wave propagation. Here this is illustrated for a few differently shaped wavefronts, where the arrows indicate the direction of wave propagation. Now in general, phase relationships for different points in space are only well defined when the waves have one specific wavelength. And if we want to do interferometry, it's vital that the light we use is of one particular wavelength, which is also called monochromatic light. And in the rest of this video I'll assume that the light used is more or less monochromatic. A frequently used way to generate monochromatic radiation is by means of a laser, and this is because the process of stimulated emission which takes place in the laser cavity favors the generation of light in a very narrow wavelength range. Also, The wavefront exiting the laser cavity is virtually flat over the aperture, and because the light has an extremely well-defined wavelength, in other words, it has a very narrow spectral bandwidth, phase relationships in the field exiting the laser can be preserved over long distances. Another way to say this is that lasers have a long coherence length, which is generally between half a meter up to several kilometers for certain special types of lasers. In practice, this means that if we take 2 points, A and B, in the light path, and we look at the variations in the phase difference between the 2 points, we will find that these will be relatively small. And the distance over which variations in phase remain acceptable is called the coherence length. As you can see from this equation, the coherence length LC is inversely proportional to the spectral bandwidth delta nu of the light source. And so light sources with a very narrow emission line will generally have a long coherence length. Another source of monochromatic light frequently used in interferometry is the low pressure sodium lamp, which mainly generates light in a narrow emission band at 589 nanometers. However, the spectral bandwidth of the sodium emission line is much broader than that of lasers, and the phase relationships generally only hold over distances smaller than a millimeter. Now, measuring the shape of a wavefront directly in the visible part of the electromagnetic spectrum is not easy, and that is because of the high frequencies involved. For electromagnetic radiation of longer wavelengths, like for example radio waves, we can measure the phase of the alternating fields directly, and that is because the oscillations have a relatively low frequency, say generally somewhere in the mega or gigahertz range. And so we can point a bunch of antennas to the sky, measure the electromagnetic signals that are received in each of them, and then establish the shape of the wavefront for a particular frequency by looking for phase correlations. And based on this information, we can identify the exact direction from which the radiation is emitted. But visible light has a frequency more than 1,000 times higher than even the highest frequency radio waves. And for frequencies this high, it's technically infeasible to measure phase directly for an oscillating electromagnetic field. However, what we can easily measure with optical detectors like CCD or CMOS sensors is spatial intensity variations, and that is where interferometry comes in. Instead of trying to measure the phase in light directly, this method works by studying the interference patterns resulting from the addition of a second wavefront that has a known shape. Let me start by showing you a very simple example of how this works in light. For this experiment we need a monochromatic light source and a flat surface. As a light source we'll use a sodium lamp, and for the surface we'll use a flat optical test glass. Now, a typical air-glass interface reflects about 4% of the incident light, and with a uniform light source we observe a uniform reflection. Let's now place two differently shaped surfaces on top of this reference surface for evaluation. And what we now observe is that these objects show two different interference patterns. The part to the left shows straight lines with equal spacing, and the one to the right displays these curved lines or circular fringes depending on the exact surface orientation. Now, it's these intensity variations that actually contain detailed information about the difference in shape between the reference surface and the two surfaces under test. And we just need to know how to interpret what we see exactly. So what do we see? Well, let me explain with an animation. I admit the following is a simplification and it's not correctly visualizing the physics, but it's actually quite illustrative. Here is a wavefront that has just reflected off a flat reference surface, so this wavefront is basically also flat. And so the image shows a 2D cross-section of the flat optical wavefront. Now, if we place a sensor in the path of the light, we can measure the intensity, and what we observe is that it's basically the same everywhere, and this tells us exactly nothing about the shape of the wavefront. Now let's add a second wavefront that has reflected off a second surface that is slightly tilted. In this example the wavefront is also flat, and what we observe is that the intensity now becomes non-uniform. And this is caused by constructive and destructive interference between the two reflected wavefronts at the second interface. Here the electromagnetic field is the linear sum of the contributions of the fields of the two wavefronts. And so in some points where these contributions are always in phase, they add up. On the other hand, in places where the two are exactly out of phase, the field contributions cancel each other out, and if they are of equal amplitude, effectively the resulting field becomes zero. In the case of two flat wavefronts, we will observe linear and equally spaced fringes. And the density of the interference pattern itself is dependent on the wedge or angle between the two surfaces. And the position of the fringes is dependent on the distance between the two surfaces. Now you might think that linear and equally spaced fringes are indicative for the presence of two flat surfaces. And that's partly correct, but two curved wavefronts with exactly the same radius of curvature will actually also display linear and equally spaced fringes when displaced or tilted. However, when two wavefronts have different radii, this results in curved fringes. And this is, for example, the case when we have a flat and a spherical wavefront interfering, or when we have two spherical wavefronts that have a different radius of curvature. So I guess it's important to realize that the observed interference pattern only gives us information about differences in wavefront shape. In the example just shown with the sodium lamp, we only observe interference between the interfaces when they're placed very close together. And that is because of the limited coherence length of the light. So whether we can see a clear interference pattern is dependent on whether stable phase relationships exist between the reflections coming off the two surfaces at the point where they start interfering. And this means that with a coherence length smaller than a millimeter, the surfaces need to be quite close to each other in order to observe interference fringes. Now, I just stated that in constructive interference, the electromagnetic fields add up, and in destructive interference, the two contributions cancel each other out. So what does this mean for intensity? Well, light intensity is equivalent to the power per unit of surface, and so it's actually not the same thing as the magnitude of the electromagnetic field. In fact, intensity scales with the square of this field, and so if we have two reflections of equal magnitude, say both are 4%, this means that for the location of constructive interference, the intensity could be 4 times as high. And that is actually what is generally observed in interference patterns, that the intensity in the bright areas is much brighter than the sum of the two individual intensities. But of course, if we look on average, the intensity over the whole area will still be equal to the sum of the two individual intensities. Anyway, enough background. Let's return to the ZYGO interferometer itself and take a peek under the hood to see what's going on inside. In order to do that, we need to remove two different lids. The outer one is made of plastic and it's basically just cosmetic, and the second one is made out of aluminum sheet metal and it is intended as RF shielding for the electronics inside. The first thing you notice is that it isn't awfully full inside. There is a helium neon laser with its high voltage power supply, then there are a few optical components like a steering mirror for a laser beam, a variable filter that can be moved mechanically using a rod, and this rod also operates a switch that activates either of two PCB cameras that can also be found in this top part of the interferometer. And the cameras, by the way, have CCD chips of about 4 by 6 mm in size and are fairly low resolution. Now, both cameras have lenses mounted in front of them, and one of the cameras is above a tiny beam splitter and the other one is above a diffuser with a crosshair printed on it. In the bottom compartment behind the lid here we find the mains, 12-volt DC power supply, a large beam splitter, a mirror under 45 degrees and a 4-inch collimation lens. And apart from a few brackets and mounts that hold the optics together, that is basically it. So you might wonder, why was this thing the price of a luxury car back in 1996? Well, apart from, I suspect, a healthy profit margin, there are several reasons. Of course, it's not really a mass manufactured item, but another reason is that every component inside appears to be of very high quality. Take, for example, the helium neon laser. According to the label, the tube has been specifically selected for this type of instrument. Why? Well, if we look at the specification of the coherence length of the interferometer, we see that it's larger than 100 meters. This means that The wavelength variations in the laser light need to be extremely low so that the phase relationships hold over distances of more than 100 meters. Now, I calculated what this means in terms of frequency stability and found that variations in the frequency of the light cannot be more than 2 times 10 to the minus 7%. And so this means that not just any random laser will do. So let me take you through the functionality of all the optical components step by step using schematics. Here is the helium neon laser, which outputs a highly coherent beam of light, and the direction of the beam can be optimized with this small steering mirror, after which the beam goes through a variable attenuation filter. Now, this filter allows for adjustment of the general brightness of the laser beam, and after having passed the attenuation filter, the beam is going into a gradient index lens, which is connected to a very small beam splitter. Now, a gradient index lens is a small glass rod that contains a gradient in refractive index that runs from the center to the edge of the rod. And since the refractive index has the highest value in the center, the optical wavefront in the laser beam is gradually delayed more towards the center of the rod. And the wavefront therefore becomes curved, which effectively results in focusing of the light into a tight focal point. And after passing this focal point, the beam expands again into a nicely spherical wavefront. A small beam splitter sends the spherical wavefront into the partially reflective surface of a second, much larger beam splitter, and this surface reflects the light towards a collimation lens where the light exits the instrument. The function of the collimation lens is to convert the spherical wavefront into a flat wavefront of 4 inches in diameter, and this flat wavefront can serve as the basis for all kinds of interferometric tests. For example, we can place 2 partially reflective flat interfaces into this output beam, one being the reference interface and one being the interface that we'd like to test for flatness. And due to the large coherent length of the light, more than 100 meters, these interfaces don't have to be necessarily very close together. The light reflecting off these surfaces is directed back into the interferometer approximately along the same path as it came from, goes through a small beam splitter again, and then is collimated and projected on the CCD chip. And this allows us to observe the interference pattern between the 2 reflections and evaluate this visually on the monitor. Now, to steer the light of both the reference and test surface exactly back through the tiny beam splitter here is pretty hard, and you don't see anything with camera 1 until things are almost perfectly aligned. So to make life a lot easier, the people at ZYGO added this alignment functionality to the system. Part of the light from the reflections can pass this larger beam splitter, and this part continues straight on, is reflected at 90 degrees angle, and then reaches the glass diffuser plate that contains a crosshair pattern. Because this diffuser plate is exactly at the focal distance of the collimation lens, the reflections create tiny spots here, and their positions can be observed by camera 2 that is only intended for alignment purposes. Now, this alignment unit has a much larger field of view, and what we can do now is simply align the position of the surface reflections such that they are at the center of the crosshair. And when that's the case, the system is also automatically aligned on camera 1, and we can immediately observe an interferogram. Now, the interferometers that I made myself did not have this kind of feature, and I must admit that this really makes aligning optics a piece of cake. Here you see the location of the collimation lens viewed from the outside of the instrument. In front of it is an adjustment mechanism that is intended for mounting various reference surfaces to the interferometer directly, like for example the f.75 transmission sphere that came with the interferometer. The adjustment mechanism has 2 degrees of freedom, which are tip and tilt, and this allows the angle of the transmission reference to be oriented with respect to the surface under test. So when testing optical components, you generally test the surface shape before the interfaces get coated. And so in the case of glass, this means that they reflect around 4% of the incident light. So the transmission reference also needs to reflect around 4% back into the interferometer to get high contrast fringes. Now, to test spherical surfaces, you need a spherical reference surface that somehow reflects 4% of the light exiting the interferometer right back into the instrument. Here I've drawn a schematic of the inside of a transmission sphere assembly to show you how that is achieved. The reference surface is the last interface of the assembly, here indicated in yellow, and all the other surfaces are anti-reflection coated for the laser wavelength. But even more importantly, they're also designed in such a way that the light reaches the reference interface exactly perpendicular, and this means that it's the only interface in the transmission sphere that sends a reflection back where it came from and then enters the interferometer as a collimated beam. And of course, 96% of the light continues on to the surface under test, which also reflects around 4%, and so we observe the interference occurring between these two interfaces. With a spherical transmission reference, we can test convex as well as concave optics. For convex optics, only radii smaller than the radius of the transmission sphere itself can be tested. And for concave optics, the only limitation for the radius to be tested is that it should be less than half of the maximum coherence length of the light source that we use, which is in this case 50 meters. Now, I want to save most of the experiments that I had in mind for another video, but let's just do one simple experiment. For this test, we'll just use the flat wavefront exiting the instrument, and what we'll try to measure is the difference in shape between the two surfaces of a zero-dur test glass. And this test glass has one side, which I know is very flat, around 1/20th of a wavelength, and this is going to be our reference interface. But the other side is somewhat less flat, and what we'll try to find out is how much that is. The two interfaces are spaced 20 millimeters apart and both reflect around 4% of the incident light. So we can just place the disc in the beam exiting the interferometer, align the position of the two reflections simultaneously, and then look at the interference pattern. And this is what it looks like. As you can see, we get a nice and clear interference pattern, which by the way is extremely stable with no effects of vibrations from the environment. And that is because the two surfaces are basically mechanically connected to each other by a solid piece of zero-dur. Now, the small circular spots are just dust particles in the optical path, and these are not important for our evaluation. All the information about the difference in shape and orientation between the two surfaces is contained in the four more or less vertical fringes. And because we know that one side is almost perfectly flat, any curvature in the fringe pattern is the result of non-flatness of the second interface. So let's try to evaluate this pattern visually. The most obvious feature is of course the presence of the four vertical fringes that indicate that there is a wedge between the two interfaces in the horizontal direction. And we can evaluate how large this wedge is based on the number of fringes. It's a little over 4 lambda wavefront, meaning that there is a wedge, half of that between the two surfaces, so just 2 wavelengths. Why half? Well, that is because in reflection, any deviations in surface shape lead to twice the deviation in the wavefront shape. And so deviations in the surface shape are only half of that observed in the wavefront. Now, since the wavelength of the laser is 633 nanometers and the wedge is 2 lambda between the two surfaces, this would mean a gradient in distance of approximately 1.3 microns. But there is a little catch in this case. Because we are comparing two surfaces with zero-dur in between them, we should actually use the wavelength in this material, which means that we should divide the wavelength in air or vacuum by the refractive index of zero-dur, which is 1.54. So this means that the wedge is actually only 840 nanometers. But which side is thicker? It's actually quite hard to tell, as for wedge we would see the same type of interference pattern in either case. So at this point, we just don't know. Okay, let's for a moment focus on the curvature of the fringes now, which indicates a difference in the radius between the two surfaces. And if we look at how much the curvature in the fringes deviates from straight lines, we see that it's largest here in the center. It's about 0.4 times the fringe spacing, which translates to 0.4 wavelengths of height difference between the edge and the center of the disc. For the surface error, which again is half of that, we find 0.2 wavelengths. Now, since we also need to use the wavelength inside zero-dur here, this means that the surface curvature is 0.2 times the wavelength divided by the refractive index, which results in a value of 82 nanometers. But in which direction is the curve? Is the surface under test 82 nanometers concave or convex? As for the direction of the wedge, there is no easy way to tell. So now we end up with these 4 configurations, of which only one can be correct. With a little logic though, you could at this point already discard 2 of these as infeasible. But of course, you want to know exactly which configuration of the 4 is correct, right? So if that's indeed the case, figure it out yourself. You just need 2 more pieces of information. Here is a first hint. If I press my finger against the back side of the disc, so the surface and the test, we can observe that the interferogram changes due to the temperature increase of the material by the heat of my finger. Locally it's only a few degrees Celsius higher, but the effect is very noticeable because we are measuring in the nanometer range. Now the second piece of information you need is about the expansion coefficient of the material. As you can see from the specifications of ZYGO, it can be either positive or negative. But this piece of ZYGO has a positive coefficient of thermal expansion, which means it expands with temperature increase. And with these 2 additional pieces of information, it's possible to tell which of these 4 options is correct. Now the first person to make a comment with the correct answer, and of course why, owns the pinned comment. Okay, so the letter was a very brief explanation of how you can evaluate interferograms visually, and the above example was actually relatively easy. Imagine your interferogram looks something like this or this. In these cases, it would be quite a bit more challenging to make accurate statements about the exact surface shape. And this is why in the next video about the subject I have replaced the current analog camera with a high resolution IP camera. And this allows for a very detailed evaluation of the interferograms using software. And with the help of this software we can measure wedges, angles, surface curvature and even the effect of warm fingers very accurately. Also, we'll take a look at how to measure the shape of various optical surfaces and the quality of lens assemblies. So hopefully I'll see you in the next video again.
Bye-bye.